Okay, in today's video, we're now going to look at a series circuit where we are now involving the power relationship, which is the power. Let's do this in black. Power of an object in a circuit, whether that's a battery that is adding energy to the circuit or some sort of resistor that is taking away or dissipating energy. Capital P is equal to the current going through that thing times the change in potential of that object. For a resistor, I know from Ohm's law, delta V equals I R, so I know for a resistor, I can say power equals I squared R, and that's me taking this and putting it in for the voltage here. So this is the general rule. This will work for a battery or a resistor or anything. This is for a resistor specifically. This wouldn't be for a battery because batteries don't have resistance. A battery would just use this relationship. All right. So again, we're going to be using our two rules, Ohm's law and this new power relationship, to answer these questions. A series circuit is shown below. It's a 100-volt battery, in case you can't read my handwriting. Now the power outputted by the battery and the power dissipated or taken away by the resistor. So I'm going to color code my equal potential lines here. So I can say before the battery, I'm going to call this, I'm going to define this to be 0 volts. Battery adds 100 volts, so this is going to be 100 as I go across this battery. When I do that, I see that that means the resistor has to be changing the potential by 100 volts as well. Adding 100 needs to be taking away 100 to get me back to 0 and conserve energy. All right, power outputted by the battery. Power equals the current times the change in voltage. So I need to find the current. How can I find the current here? Well, I'm going to look at my relationships here and I can say, well, this involves current. They both involve current. I can't use this one right now because that's what I need to do. It tells me the change in voltage is I, the current, times the resistance for a resistor. So I say, well, I know about this resistor. I know this resistor is changing the voltage by 100. I know its resistance is 20 ohms, so I can find that the current for this resistor, delta V equals IR. It's changing it by 100, I times 20. The current is going to be 5 amps. All right, so now I can find, that's the current here. 5 amps is going through this resistor. Current is the same everywhere with one loop. It's not splitting up. So it's going to be 5 through the battery as well. 5 amps, 100 volts, equals 500 watts. Determine the power dissipated by the resistor. Conservation of energy tells me the battery is adding 500. I only have one resistor, and that resistor has to be taking away, dissipating 500. So B. Also, if I technically it would be negative 500. I guess you could say. If I'm saying the system is the whole circuit, it's taking away 500 watts, 500 joules every second away from this system. All right. A light bulb has a power rating of 60 watts. It's plugged into an outlet that produces a potential difference of 110 volts. What resistance do I need in this circuit? So it's just looking for the overall resistance, so I can pretend I have this sort of deal, 110 volts. simple circuit, my equivalent resistance here. What does that need to be? And I have a power of 60 watts for this light bulb. Okay, so, sorry. I got power equals I delta V, or power equals I squared R. And we're just gonna, I think, assume that the light bulb is the resistor, only resistor in the circuit here. It's the way we're gonna have to do this. So 60 watts equals I squared R. Oh, that doesn't tell me what I want. I gotta back up. I delta V. The reason I have to do this is I don't know the current or the resistance, but I do know the voltage. And the voltage that the battery is giving has to be the same that this resistor takes away, because it's just one resistor and one battery. So 60 watts equals I times 110 volts. So I should have made that 120 volts to make this math a little easier. Next year, maybe. 60 over 110. 6/11ths, whatever that is. 0.54 amps. Well, now that I know that, I can go back to Ohm's law. Delta V equals IR. 110 volts is what this resistor needs to change. The voltage by equals 0.54 R. So R equals 110 over 0.54. It'll be like 200 something or other. 204 ohms. I could go back and double check that. I know P equals I squared R, so if I did I squared times 204, I should get 60. Power dissipated by R2 is 6 watts, so let's write that with R2, it's 6 watts. Determine the current through the circuit. It's going to be the same everywhere because it's one loop. So let's color code. We'll say before the battery is 0 volts. After the battery would be 16. And this would be something between 0 and 16. I don't know what it is right now. All right, and we want to know the current. Well, looks like I know two things about this resistor, and we'll find as we go along that as long as I know two things about something in a circuit, I can find the rest of the things about it. So I know the resistance, I know the power. I should be able to find the current. So power equals I squared R. That can get me there. If I only had my original power equation, P equals I delta V, I could start here with this, so why don't we do that? It's a little bit longer, but good practice. So 6 watts equals, wait, I can't start here, I don't know the current, I lied. I do have to go to this first. 6 watts equals I squared 1.5 ohms. So I divide 1.5 on each side. And I end up with 4 equals I squared. So I equals 2 amps. Great. And that's going to be the current everywhere here. So I can go back. This is 2 amps. All right, so A, 2 amps. B, determine the power outputted by the battery. So now I'm looking at my battery. What do I know about the battery? I have 16 volts as its potential difference. It's changing it by 16. And I know there's 2 amps of current going through the battery. So I can say for the battery, 2 amps, 16 volts, 32 watts, 32 joules per second. C, determine the resistance, potential difference across, and the power dissipated by R1. So figure out everything there is to know about R1. Well, I know the current through it is 2 amps. Now there's a bunch of ways I could go about this. I could really solve any of these first. Let's start in the order it's given, I guess. Determine the resistance. I might end up finding other things in order to do that. 2 ways I can do this. I can think of this in terms of conservation of energy, and I can think about the voltage change across each of these resistors. So this is way 1. We'll do way 1 in orange. I can look at this, and I know battery's adding 16. Can I figure out how much R2 is taking away? Because I know a lot about R2. I could say the delta V is IR. So delta V for R2, 2 amps, 1.5 ohms, 3 volts. So from here to here, from one side of this to the other, is a change of 3 volts, which means this blue area, I can now say what it is. Because I know this is 0, I said this was 0. That means this has to be 3, because if I go from 3 to 0, that's a change of 3 volts. Why was that useful? Maybe I didn't know why it was useful, but I knew it was something I could do. And now I say, oh, hey, that's cool. That's a change of 13 volts. So that's equal to IR, where I is 2 amps, R is the resistance. So we get R has to be 6.5 ohms. So there I found the resistance. Now, and in doing so, I found the potential difference across 13 volts. And the power dissipated by R1. So power equals I delta V, or I squared R. Either one would work. I have enough information to do either. But 13 times 2 is easier math for me to do. 26 watts. All right, so that's the one way I could have done this. The other way, instead of doing all that, is I could have said the battery I found was 32 watts. This resistor is 6 watts. So the battery's giving 32, this is taking away 6. That means this has to be taking away 26, because 32 minus 6 is 26. And then I could have worked backwards and found these other things. So I could have started with knowing the power is 26 watts. I could have used that with the current to find this had to be 13 volts. I could have used that with Ohm's law again to find 6.5 ohms. let's write these out. R equals 6.5 ohms. Delta V equals 13 volts. Power equals 26 watts. Household appliance requires 270 watts, has a resistance of 120 ohms. What potential difference should we put across the appliance? This is a simple circuit question. One battery, one appliance. I have P, I have R, I want to know delta V. P equals I delta V. Well, that doesn't help because I don't know this or this. So let's try this. I squared R. Well, I know that. I don't know that. I do know that. I do know this. So let's plug those in. 270 watts equals I squared 120 ohms. 270 over 120. 27 over 12. That's not a nice number, is it? 27 over 12, those are both divisible by 9 over 4 equals I squared. That's not so bad. So we take the square root. That's 3/2 is the current, amps. That's not what I wanted though. I wanted the potential difference. So I can now use Ohm's law, V equals I R. 3/2 amps, or 1.5 amps. So 120 ohms. That's 180 volts. My battery powering 2 light bulbs in series will die more slowly than a battery powering just one of the bulbs. So let's draw each situation. One light bulb versus two light bulbs. Same battery. We'll assume each light bulb is the same resistance, same voltage. So what's different about these two situations? This one has twice as much resistance. So I know I can add these to find the total resistance because it's a series circuit, one loop there. So this is going to have a current of I. This one, the current would be half of that, twice the resistance, half the current. And we're talking about power here. We're talking about time more slowly. So let's look at the power from each battery. Power equals IV, I delta V. All right. So I can see for this one, it's just I times V. For this one, the power the battery has to output, it doesn't have to output as much because it does not need to create as much of a current. It does not need to put as many coulombs per second through it, which means it does not need to output as much power. This one's just I delta V. This one's I over 2 delta V. So we can see in the case with more bulbs in series, we get less current. So we end up needing only half as much power from the battery. And if you remember from the simulation, these bulbs will be a lot dimmer than just this one bulb. We're running out of battery here. Speaking of, Series circuit with an unknown resistor is shown below. Determine the resistance R2. So the power outputted by R1 is 320 watts. And here I already wrote that down. If I hadn't, I would have written it. Determine the power outputted by the battery. And the resistance. Okay. Throw some colors on here. Because that's just what we do. To help see what's happening, help us solve this logic puzzle. So I've got some electrons where I'm going to say they're at ground level, no potential. Battery ski lifts them up till they're at 100 volts. They fall over this resistor, they lose some of those volts, I don't know how many. They still have some energy. And they lose more, going back down to 0 across this resistor. All right, so let's see what I can figure out here. I have the resistance, I have the power. What can I do with that? Well, I can find the current through this resistor with those two pieces of information. (32 divided by 2 is 16. 4 amps. All right. Does that help me? Maybe, probably. So 4 amps is going through this resistor, which means 4 amps is going through this whole thing, because it's one loop. Can that help me find out something about R2? I don't know anything about R2. Well, now I know. Now I know one thing about R2. I know the current going through it is 4 amps, but to figure out resistance, I need to know at least 2 things. Because I look at my equations, and all my equations involve 3 things, so I need to know 2 to figure out the third. So I need to either know the power from this guy, or I need to know the potential difference in order to find this resistance. Let's do it both ways. How could I find the potential difference, the change? I would need to know this blue area, how much the potential is here. Can I do that? Can I figure out how much R1 is changing it by? Then I know what that is? Yeah. I know delta V. Just gonna write it under here because it's the same resistor. 4 amps, 20 ohms, 80 volts. So now I can say the blue is 20, not 80. 80 is the change. 100 minus 80, 20 volts. Great. So this resistor then has a change of 20. It's taking it from 20 down to 0. Can we get there? Delta V for this resistor is 20 volts. The current is 4 amps. So 20 volts, delta V equals IR. R2 has to be 5 ohms. Okay, cool. So A, we said 5 ohms. B, power over the battery. Power equals I delta V. 4 amps, 100 volts, 400 watts. So again, another way, I forgot to say we'd do it both ways. Another way we could have solved A here is we could have done this part first. 400 watts. It's adding. Resistor 1's taking away 320 watts. that means that the power for this one has to be 80 watts dissipated. Adding 400, take away 320, still have 80 left. And this R2 is going to do. And from there, I could have done 80 watts equals I squared R. This again was 4. So I could have gotten R was 80 over 16, which is 5. Right? Because this idea that we used here that the voltage all around has to be 0 is the same idea, really. They're both conservation of energy, that the power from the battery has to be equal to the power taken away from both resistors. Cool, we made it. Didn't run out of battery. Excellent.